spectroscopy with a synchrotron beam where you get down to very small scales. And they determined that actually the ferrous iron content over ferric iron is only 0.84, or about 16% ferric iron, or an FO2 that's actually higher than QFM. Okay. And this is the number that made me think, is that for reasons I will show you, that there really is a crisis. Okay. If this is the number, then I have a lot of problems that I'm going to share with you in the next few minutes. Okay. But the reason one reason there may not be a crisis is that at Goldschmidt this summer, when I gave this talk, a version of this talk, everybody came up to me and said, no, the number's not actually 84. The Minnesota group has redone the Mossbauer spectroscopy that was involved in the calibration using cryogenic Mossbauer spectroscopy at low temperature, and they decided that actually the number is swinging a little bit back. And Andrew Berry has decided that one of the components of the Mossbauer spectrum has been completely misassigned to Fe3+, and it's actually Fe2+, and the number actually goes all the way back to 0.88. If that's true, then there's no crisis. Okay. So just to show you graphically these differences, this is a figure from Christie. This is the number here. This is ferric iron over total iron. There's the 0.15, about half a log unit below QFM, that everybody believed based on hole rocks. And then this was the number that came out from the glasses. Okay, we go all the way down to 0.07 ferric iron and significantly below the QFM buffer. And then this is the figure from Bezos and Hummler. The open symbol is the Christie histogram, so we shifted back this way for Bezos and Hummler to about 0.12. And something interesting came up in Bezos and Hummler's description of the various analytical issues. And this table shows you analyses of Fe2+ in a standard rock powder, BCR1, it's a Columbia River basalt that the USGS ground up a ton of and gave out to everybody as an analytical standard. And everybody who's analyzed it from 1969 through 2005 gets basically the same number within about 1%. Okay. So the methods seem to be good. But on the other hand, JDFD2, a very glassy pillow rind from the Juan Fuca ridge, these are the analyses, and they vary from 10.5% to 11.12%, way more than 1% difference. Same method, rocks with about the same iron content. For the rock powder, they agree. For the mid-ocean ridge salt glass, they don't. So one possible reason for that is the presence of microphenocrysts in the rock, but nobody's quite sure why these analyses don't agree. And then the Zanes measurement, which is based on this spectrum of absorption of X-rays near the iron K edge, which is sensitive to the chemical state of iron in the sample. There's one peak at this energy, which is characteristic of iron 2+. There's another peak at this energy, which is characteristic of iron 3+. And Cottrell and Kelly calibrated the centroid energy of this pair of peaks versus the ferric iron over total iron by wet chemistry. And the calibration runs all the way from air, which is essentially all ferric iron, down to about 10% ferric iron. And you can see on this plot, zoomed in here, this is the Cottrell and Kelly calibration, and then these are the Bezos and Hummler numbers, and these are the Christie numbers down here, and that's the disagreement. Okay, and so here's, everybody likes to plot a histogram with the same information, so you can compare them directly. Here's Cottrell and Kelly's histogram, and here you see the Christie histogram, the Bezos and Hummler histogram, and the Cottrell and Kelly histogram. There's very clear shifts in the mean and almost not even that much overlap in the tails. So in this talk, I do not want to spend my whole time arguing about the analytical issues. I don't actually know that much about the analytical issues. It's not what I do. You actually have people here who really do know about the analytical issues, and so you should go harass Gordon, and you should go harass Becky, and let them explain to you what they think is the truth. What I do want to talk about is the consequences of these estimates of the oxidation state. Okay? The debate has mostly been posed in terms of what do we know about the oxidation state of the Earth's mantle? What do we know about the cycling through time of subducted oxidized material from the surface and mixing it back into the upper mantle? Okay? I want to deal with a different set of consequences, which is when you change your estimate of the oxidation state of the salt glass, you are changing your estimate of the ferrous iron content, which affects almost everything about the petrology of those rocks and how we infer things like what was the liquidus temperature, and are there phenocrysts actually phenocrysts, and how much did the mantle melt in order to create those rocks. And that's what I want to go through, okay, is how these dependencies work. And I'm actually going to go so far as to make the claim that based on petrological inference and what I think I know about the way the world works, I can decide which of the analytical techniques is right and which one is wrong. That might be pushing it a little bit. But let's see whether you believe it. And so here is the old story. Before Cottrell and Kelly came along, I would say we had a nice and consistent story for how the whole mid-ocean ridge system works. And it goes like this. We start with a depleted mid-ocean ridge mantle source composition, a peridotite whose composition we think we know, that is complementary to the extraction of the continental crust from the primitive mantle. It's a pretty well-defined composition. And if it upwells beneath the ridge at a potential temperature, which is just a way of describing which adiabat we're on, of 1360 degrees C, it will start melting at a depth of about 70 kilometers. It will melt to an average extent of about 10% by the time it reaches the base of the crust. If you take out that 10% melt from a 70-kilometer mantle section, you make 7 kilometers of oceanic crust. Okay? And the melting models say that that primary liquid that you get by melting peridotite to 10% will have about 13 weight percent magnesium oxide, and it will be in equilibrium with a residue left behind in the mantle that has a magnesium number, magnesium over magnesium plus iron, of about 0.91. And these two things are in equilibrium with each other, and this is what you actually observe in abyssal peridotites. You then take that primary liquid and you start cooling it and fractionating it in the crust, and you cool it and fractionate it by about 50%, leaving behind a cumulative lower crust of dunites and troctolites and gabbros, until you get down to the liquid composition that corresponds to what we actually sample on the seafloor, the volcanic sequence. And you end up with a crust that mass balances nicely with 2 or 3 kilometers of volcanics and 3 to 5 kilometers of cumulates. And so in this story, you can make a single model where a certain mantle source composition at a certain potential temperature gives a certain extent of melting, which yields a primary melt that requires a certain extent of fractionation. And when you do those things, you fit the thickness and the composition and the seismic velocity of all of these layers. Okay? That's nice. That's great. And there's pretty good agreement on what the potential temperature has to be to make this work. So this is an old figure from a version of this model that I put together, where I showed that the potential temperature, how hot the mantle is, versus the crustal thickness in kilometers that you get out of it from either the Langmuir model or Rowe-Kinsler's model or the original Meltz model. They all agree pretty well that you get normal thickness oceanic crust, which is 7 plus or minus 1 kilometers, for a potential temperature somewhere in the upper 1300s. Okay. There's a lot of differences between these models, but on this they agree. Okay. Actually, there's a newer version of the Meltz model, the P-Meltz model, okay, which shifts this by 20 or 30 degrees or so. But still, in order to get normal thickness oceanic crust, you need a potential temperature in the upper 1300s. And one thing these models all agree on very nicely is the slope here. For a 25-degree change in the potential temperature of the mantle, you get about a 1 kilometer change in the thickness of the oceanic crust that comes out the top. So, what does the redox state have to do with all of that? What changes if you come along and tell me that the ferrous iron over total iron is different from what I thought it was? Okay? The reason this matters is that nearly all of our petrological insight into how basalts work and our ability to infer temperatures from them comes from olivine liquid equilibria. Olivine liquid equilibria are the thing that basalt petrologists understand best. Okay? Olivine is the first solid phase to crystallize from terrestrial basalts as they cool. It's ubiquitous in basalts. Okay, here's a green sand beach from Hawaii, just a big pile of olivine. Okay? And olivine liquid equilibria are pretty simple and pretty predictable. And the fundamental basis of our ability to predict olivine liquid equilibria is this magic number, K sub capital D. Okay? KD, or the exchange coefficient or the distribution coefficient, is the number everybody has been using for, well, about 45 years to describe how olivine liquid equilibria work. It's a very systematic, well-behaved number. Okay? And it is the ratio, if you actually want to know what KD is, it's the ratio of the olivine liquid partition coefficient for FeO to the olivine liquid partition coefficient for MgO. Okay? Or if you want to rearrange it a little bit, it's the FeO-MgO ratio of the olivine divided by the FeO-MgO ratio of the liquid. Okay? Or if you want, you could express it in terms of the magnesium number of the liquid and the forced direct current of the olivine. The point is, this is FeO, iron 2 plus, and only iron 2 plus that appears here. It's not total iron. Okay? And so if I change the amount of FeO that I think is in a rock, where I've analyzed total iron, but now somebody comes along and changes their estimate of the redox state, okay? That changes this number here, which changes the KD, unless I go and I change the iron content of the olivine to compensate for that. Okay? And this has been known since at least 1970, that this number is a systematic function of the ferrous iron content of the liquid. Okay? But it's so easy to measure total iron that people seem to have forgotten this. And a lot of what's out there in the literature is based on an apparent KD where the FeO is replaced with FeO star or FeOT, which is total iron. Okay? And I argue that there's no reason that that should be systematic in any way. If it appears to be systematic, it's because you sampled it over a limited range in FO2. And people do indeed do most of their work over a very limited range in FO2. The gross majority of the experiments that people use to calibrate their melting models are done at QFM. But you can go all the way back to Roeder and Emsley 1970, where they did experiments across a very wide range of oxygen fugacity from air down to iron leucite. And this is the same liquid composition at the same temperature, and this is the composition of the coexisting olivine. In air, it's forced to write 96 because there's so little FeO in the liquid to equilibrate with FeO in the olivine. At iron leucite, it's forced to write 75. There's lots of FeO in the liquid, so you get lots of FeO in the liquid. Okay? This is the systematic behavior that we should expect. Okay? So, we're now going to unpack this diagram in considerable detail. All right? So, buckle your seatbelts. This is a graph of FeO, not total iron, but FeO in the liquid and weight percent, versus MgO in the liquid and weight percent. Okay? And these straight lines, the straight diagonal lines here, are constant ratio, okay, of iron to magnesium in the liquid, which is a given value of the magnesium number. And for simplicity, I've constructed this diagram using a constant value of KD of 0.3. Okay? This number actually varies a little bit. This laser pointer died, as laser pointers always do. Is there a stick? Yes, there's a stick. I prefer a stick. For simplicity, I've constructed this diagram with a constant KD of 0.3. Okay? And that means whatever the magnesium number of the liquid is, it's in equilibrium with an olivine of a given composition. And I can construct the olivine compositions that would be in equilibrium with a liquid anywhere on this diagram. And also for simplicity, at this point, I've assumed that the residual olivine left behind in the mantle at the end of the mantle melting process has forced to write 91 olivine, which is approximately right. Okay? So, let us imagine that we pick up this particular rock from the Mid-Atlantic Ridge, and we analyze it, and we find it has 9 weight percent MgO, and it has 8.7 weight percent total iron based on the electron probe analysis of the class. If we pretended that all of that iron was FeO, it was fully reduced, okay, then that liquid would be in equilibrium with forced to write 86 olivine. And if we add some forced to write 86 olivine into it to correct for fractionation, it will evolve this way until it's at this composition in equilibrium with forced to write 87 olivine, and so on back along this olivine control line, which is a curve, not a line, until you get back to equilibrium with mantle olivine way up here at 15% MgO in the liquid and a liquidus temperature of 1350 degrees. Okay. However, if you started with your analyzed glass and you said, oh, wait a minute, that measurement of total iron is not all FeO, some of it's Fe2O3, then you're going to start from a point somewhere down here. And here's three different places you might start from. You might start from the Christie et al. Number. You might start from the Bezos and Hummler number.